that we learned was the Hess law of constant heat summation. So we have written what is the Hess law of constant heat summation. So if you are asked what is the Hess law of constant heat summation, that you can write that equation. But let us see where it is used. So it is used in reactions such as if you have A and it is giving you B, B is giving you C, C is giving you D, okay, D is giving you E. So if you have these reactions, okay, you have these reactions and you want to calculate and you have been asked to calculate these are all thermochemical equations. It means you have been given delta H1, delta H2 for this reaction. This is the delta H3. This is the delta H4. So all of these enthalpies are given and you have been asked to calculate the enthalpy of reaction A to E. You have been asked to calculate the yes, for A to E. Then what you will do, you will just add them, right? I'm just going to add them. And you can see that if I am adding these things, then I will cancel B, C, C will be cancelled, D and D will be cancelled. And you will get the net reaction A is giving me B. So delta H naught R will be equal to, since we have added all of these components, all of these reactions, I will add the enthalpies also, H1, delta H2, delta H3 plus delta H4, right? So the sum of these, that is why the Hess law of constant heat summation. So whatever heat we are summing up, that is equal to, that will be equal to the enthalpy of reaction that we are doing. But again, it will not be very simple like always. It will be plus plus plus. For example, you can also have something like, let me say, 2A giving you B. 2A is giving you B. This is the target reaction that we want to calculate the enthalpy of. Okay. Now here you have some reactions that are known to you, and the enthalpies for that enthalpies of those reactions, they will be simple reactions, okay, and their enthalpies can be easily found in the data. And many scientists have worked on these reactions and they have calculated their enthalpies. So you have A to B with delta H1, then you have B to C, delta H2, C to D, delta H3, right? And then you have here, you have a reaction E to F, in which you have delta H4. Now, in this case, if you are going to add them up, then you are not going to get, because here you have, at this side, the reactant side, you should have 2A giving me E. But if you are going to add this up, then all of these things will get cancelled, right? All of these things, you say that E is giving you D. This is the reaction that you are having, okay? All of these things will be getting cancelled, but you will not get 2A giving me E. So you will have to make some changes. First of all, you will have to multiply 2 here, right? You will have to multiply 2 here and do something. So say this is 2B giving C. So you can cancel that out. And then you have to reverse this reaction in order to make it D is giving me E. So when you're reversing that reaction, that means you're also changing the sign of this enthalpy, It will be better that we write a question and we will try to do and solve the enthalpies. So write the question, calculate the enthalpy of formation, calculate the enthalpy of formation of ethane from the following data. Okay, from the following data. So you have some reactions given, which are given carbon plus O2 will give me CO2. And all of these are gases. And the enthalpy of this reaction, it is going to be equal to minus 393.5 kilojoule per mole. Please write this question with me. Second, you have been given H2 plus half O2 is going to give me H2O. And the enthalpy of this reaction is equal to minus 286 kilojoule per mole. Third reaction they have given is the enthalpy of combustion of ethane. Here you are having 7/2 O2. It is going to give you 2 CO2 plus 3 H2O And the enthalpy of this reaction, it is equal to minus 1560 kilojoule per mole. Okay, so this is the complete question. This is the complete question. Now we are going to solve this. So write this down. Please let me know if you're done writing the question.
Done, sir.
Done, all of you? Yes or no?
Yes, sir.
Okay, fine. So you tell me, calculate the enthalpy of formation of ethane. What are we forming? What we have to form? So whenever you have enthalpy of something, I think I have told you, this enthalpy of formation will correspond to a particular thermochemical equation. Right, guys? Yes or no? Enthalpy of formation, if you look at your notes, then there is a specific way of writing the enthalpy of formation of different substances, right? We learned this in the last class, right, Hannah? So yeah, now you tell me, what is something that we are forming? What is the substance that we are forming? Enthalpy of what? Enthalpy of formation of ethane.
Ethane.
What is the formula for ethane? Formula for ethane?
C2H6.
C2H6. Hannah? Now you tell me, how do we write? So the questions that you have to ask is, what are we forming? Now, when you know what are you forming, then you will look at the elements and you will ask yourself, what are the elements that are forming ethane? So what are the elements that are forming ethane?
Carbon and hydrogen.
Carbon and hydrogen. Now, carbon is present in what state? In what form? In what molecular formula? If I want to have carbon in nature, how will I get carbon in nature? In the form of graphite, right? So it is carbon solid. Only carbon. Yes or no?
Yes, sir.
Okay. And hydrogen. How do I get hydrogen in nature? In what form? It is gas, but what is the molecular formula? Yes, somebody said something. H2, very good. H2. And then what you have to do, you have to the stoichiometry. So you will write 2 carbon and H2, how many hydrogens? 3 hydrogens, right? Gas, it is going to give me ethane, which is gas. And this is the delta H0 formation. This will be some value here, right? Okay. Now all of you have written this equation, and I hope if you have not been asked formation, if you have been asked anything, I hope you all can write the enthalpy of that particular substance. Yes or no? For example, here formation is given, so you are going to write easily for formation. Similarly, if combustion is there, you can write for combustion also. If it is something else, then you can write that also. Okay. Fine. Just wait a second. Let me wait a second. I'm getting a call. Yeah. Okay. So all of you have written this reaction, and this is what we are going to call as target reaction. What reaction? What reaction, guys? Target reaction. Because we have to move towards this reaction. Now we have 3 reactions that has been given to us. We have to arrange these 3 reactions in order to get the target reaction. Now I have numbered 1, 2, and 3. So first of all, you will look at, you can be given any n numbers of reaction. You will look at the first reaction that is given. Don't lose your focus. Be focused on each thing. As you read the question, enthalpy of formation, you are going to write the equation. Next thing is that you're going to look at the first equation, and then you will ask yourself, is there anything common between this first reaction and the target reaction? Is there anything common? Anything in the sense that any chemical species that is common?
Yes, sir.
Yes, what is common?
The carbon and hydrogen and ethane are all present in each.
No. What is common?
Carbon.
Okay.
Oxygen.
Only carbon, right? What else?
Yes, sir. Only carbon.
Parvati, only carbon, no? The first reaction and the target reaction. I'm asking in the first reaction. Can you read the first reaction? Read the first reaction.
Only
the
in the
first
first
reaction.
reaction. Okay.
Only carbon, right?
Yes, sir.
Okay. And in the target reaction and the first reaction, carbon is on the reactant side. Yes or no? It is on the reactant side in both of them.
Yes,
Yes.
Yes. So we'll write that reaction as it is. You will write that reaction. Now you just make a mark here that we are not going to do anything with that. That is our target reaction, and we are writing the first reaction as it is. With its enthalpy. Okay, with its enthalpy. Now, there is not something very quite similar with the first reaction that we have written and the target reaction. And the point of difference is that here we have only one carbon in the given reaction, and in the target reaction we have two moles of carbon, right? So what I will do, I will multiply this whole equation by 2. So I will write 2 carbon molecules and 2 oxygen molecules are giving me 2 molecules of CO2. And if we are reacting 2 moles of carbon, then I will have to multiply this H0 also into 2. Yes or no? Tell me, guys.
Yes, sir.
Because if I had
Yes.
1 mole, then it was giving me minus 393. When I have 2 moles, then it will be giving me double amount of heat, right? Double amount of heat. Okay. Now tell me for the next reaction, what is common between the second reaction and the target reaction?
Hydrogen.
Hydrogen is common. Okay. Now hydrogen is on the same side in both of these reactions.
Yes, sir.
Yes.
Right? Both of hydrogen was in the second reaction, it is on a reactant side, and on the target reaction, it is also in the reactant side. But what is not common? The stoichiometry, right? Yes or no?
Yes.
The stoichiometry here it is 1, and in the target we need 3 moles of hydrogen. So what we will do, we will multiply the whole thing, the whole reaction by 3, and we will write 3H2 plus 3 by 2 O2 is going to give me 3 moles of H2O, and the enthalpy of this reaction, it is going to be equal to minus 286 kilojoule per mole into 2, right? Yes or no?
No, sir.
Yes.
No.
10 to 3, right?
Into 3.
Ah, sorry. Thank you. Into 3. Now, the next is the third reaction and the target reaction. What is common? What is common between them?
Ethane.
Ethane is common. But is ethane on the same side in both of these reactions or different side? Different, right? So what we will do, we will reverse this reaction. We will reverse this reaction. We will write 2 moles of CO2 plus 3 moles of H2O is going to give me what? Is going to give me C2H6 plus 7 by 2 moles of O2, and the enthalpy of this reaction. Now, when we have reversed this, so if I was going from A to B, I was getting minus this much joules of energy. But if I'm reversing this reaction, then I will have to put the same amount of energy, right? So since we are reversing this reaction, the sign of this enthalpy will also be reversed, and it will be 1560 kilojoule per mole. Makes sense, guys? Yes or no? Does this make
Yes,
sense,
sir.
or do I need to explain it a bit more? Make sense, all of you?
Yes.
Yes.
Okay. Thank you. So now what we need to do, we just need to add them up. You have to arrange them, and at last you just need to add them up. Okay, so you just need to add them up. So this is our target reaction. Don't add that target reaction. And you see 2 moles of carbon. Okay, so I can't see anything in the reactant side here, so I will write 2 moles of carbon plus, here we have 2 O2 and here we have 3 O2. So if I will add them, what will be the sum of 2 O2 plus 3 O2? 2 O2 plus 3 O2 will be equal to how much?
7 by 2.
7 by 2 O2. So just tell me, are you comfortable with this?
Yes, sir.
What about others?
Yes.
Yes, sir.
Yes, all of you, na? All of you, yes or no?
Yes, sir.
Yes, please let me know if you have any problem with this cancellation. I can explain that. Okay, then 2 carbon, and then here we have, okay, so I can also eliminate this H2O, right guys? I can also eliminate this CO2, correct? And at the end, what I'm getting is 2 carbon plus 3 moles of H2 is going to give me a mole of C2H6. This is the target reaction that I wanted, yes or no?
Yes.
Yes or no? So now the enthalpy of this reaction, that is the formation, it is equal to 2 times into minus 393.5. All of this when I will add, and I will write at the end kilojoule per mole, plus I will write 3 into minus 286 plus 1560, and if you add them all up, multiply these things also, this will be equal to kilojoule per mole. So please write this down. So I think I need to scroll up or something. So you have written the question, just need to write the solution. Write this and tell me what is the enthalpy of formation. Okay, let me wait for other answers also, Parvati. Okay. Yes, I think Maimuna, you are more near. एक second, but Maimuna, it will not be like 0.4 तो कहीं से नहीं आएगा. I think so. If I look at the, it won't be 0.4, I think. Okay. And Parvati, you just recalculate now. I think you are messing up somewhere. Yes, correct. So all of you must be getting minus 85 kilojoule per mole. Yeah, all of you are getting the same thing, right? Okay. So I hope all of you understand now how to deal with different, if you have the data given of different reactions. So first thing is that whatever you have to find out. So in this example, it was enthalpy of formation. So you will first of all write the equation, thermochemical equation corresponding to that reaction. And then you will look up to the data and then do the same thing. First reaction, what is common? If that is common, then if the stoichiometry matches, then don't do anything. If the side matches, the reactant is also on the reactant side here also, then don't do anything. If the stoichiometry is not matching, then multiply or divide by some number. And then if the sides are not matching, then reverse it. So, but if you're reversing it, whatever you are doing with the reaction, you should also do the same thing with the enthalpy that is given in the data, the enthalpy that is given in the data. Okay. So since we have learned only enthalpy of formation, I think, did we learn anything else? Enthalpy of reaction and formation. Enthalpy of formation we have learned, right? Enthalpy of formation and standard enthalpy. So what we will be doing now, because in these type of questions, you need to write the thermochemical equation corresponding to that enthalpy, whether it is enthalpy of formation or combustion or neutralization or anything else, you will have to write the enthalpy of that thing. So first of all, we will look at some common enthalpies. Okay, so common enthalpies are two main common enthalpies, that is formation, and the next one is combustion, that we are going to write. So you guys write with me. Enthalpy of different types of reactions. Hai na? Arey, don't write with me, okay? Just look, don't write please, okay? Just listen. Enthalpy of different types of reactions. Please listen, huh? Don't write. Please listen. Enthalpy of different types of reaction. The first formation that we have done, it is one of the most common. The second most common is standard enthalpy of combustion. That is delta H naught C. Delta H naught C. So enthalpy of combustion, the enthalpy change per mole, enthalpy change per mole of a substance when it undergoes combustion. When it undergoes combustion. Okay. And also write the heat exchange, the heat change accompanied with the heat change accompanied by combustion of one mole of a substance. Okay, so whenever we are writing the standard enthalpy of anything, then we will have to write 1 mole of that substance. Okay, 1 mole of that substance. For example, to start with CH4 plus O2, it is going to give you CO2 plus 2H2O, right? So this is a reaction that corresponds to enthalpy of combustion. You can also have C4H10 plus O2. It is going to give you again CO2 plus H2O. But how much H2 and how much CO2? So you will be getting 4 CO2 molecules, right? And how much H2O you will be getting? You will be getting 5 moles of H2O. Okay. Now you just balance everything. Don't balance this part. This will be 1 mole only. This is going to be 1 mole no matter what, because the definition says that enthalpy change per mole, per mole. So this is not going to change. C4H10, the stoichiometry is not going to change. Now, how many oxygens do we need? We have here 4 to the 8 and 8 plus 5, that is 13. So you will have 13 by 2 O2 molecules. The stoichiometry of O2 will be 13 by 2. Okay. So no need to worry about this type of fractional stoichiometry. It is just because we need to have only 1 mole of the substance. 1 mole of the substance. Write next. No, don't write next. So all of you understood this? Yes or no? How to write the enthalpy of combustion, the reactions?
Yes, sir.
Huh, guys? Okay, yeah, that is more important. You must know how to write the reaction. Next is standard enthalpy of atomization, which is represented as delta H naught A. Delta H naught A. Now, standard enthalpy of atomization, in which what will happen? I'm writing some H2. It is going to give you H2 gas. If you have CH4, it is going to give you carbon in gaseous form plus 4 hydrogen also in gaseous form. If you have sodium solid, that will be given to you in sodium gas form. Okay. So what we are seeing here, we are converting a substance, a molecule, a compound into its individual. So यहाँ पे हमने H2 ही लिख दिया. Sorry, this will be 2H. 2H gas. To its individual components, to its individual elements in gaseous state. Okay. So the enthalpy change accompanied, and also here one mole. Huh? Please, you can see the enthalpy change accompanied. The enthalpy change accompanied in conversion of 1 mole of substance, 1 mole of substance into its individual elements in gaseous state. In gaseous state. Okay. So all of you understood this? Yes or no? If you have to write the enthalpy of atomization, can you write the reaction? Yes or
Yes,
no?
sir.
Okay.
Yes.
See, you don't have, see, never, whenever you are thinking about standard enthalpy of atomization, the reactions should come in your mind, never the values. And values are not important to you. Values are not important to, they are important, but not to you. They are important for those who are doing some experiments and all. So they have to look at the value for understanding, and for the conceptual part, what is important, the reaction that correspond to a certain enthalpy of something, atomization or formation. What is the reaction that represents that enthalpy? Okay. Next is bond enthalpy. Next is bond enthalpy. So we have written how many? We have written 2. So we'll have the third one, that is the bond enthalpy. Bond enthalpy. And this is delta H naught, whatever the bond is. Okay, whatever the bond is. If you have HH bond, then we will be writing H bond H. So this is what, this is simple. The energy required to break 1 mole of a particular bond. 1 mole of a particular bond. Please remember, this is related to a bond. It is not related to any substances. Okay. This is related to what? This is related to what, guys?
Bond.
It is related to bond. It is not related to any substance. It is not related to any substance. Please remember. See, if I have CH4 and I want to write the bond dissociation energy, then in this I will be breaking the bonds. I will be forming carbon and hydrogen, 4 hydrogens, right? 4 hydrogens. But what do you guys think? Is this the bond enthalpy? No, because what we are doing here, we are breaking the CH bond. Okay, we are breaking a CH bond, and in 1 molecule of CH4, there are 4 CH bonds. So in this case, what we are doing, we are breaking 4 CH bonds. Okay, we are breaking how many bonds? 4 moles of CH bonds. So this does not correspond to a good, this is not the corresponding equation for bond enthalpy. Okay, for bond enthalpy. So first of all, let us classify this into 2 different types of molecules. We will have 2 different types of molecules. We can either have let me write bond enthalpy. In this, we can have 2 different types of substances. If you have a diatomic substance, then in this case, we call the bond enthalpy as bond dissociation energy. Bond dissociation energy. And it is quite simple. If you have diatomic, that means if you are taking H2, then 1 mole of H2 bond, 1 mole of H2, it has how many bonds? It has 1 mole of HH bonds. 1 mole of HH bonds. So these type of substances are pretty easy to calculate. You can just write H2 gas and it is going to give you 2H gas. And whatever the enthalpy will be, we'll write delta H naught HH bond. If you have Cl2, then you can write 2 chlorine gas, delta H naught Cl bonded to Cl. You can also write for Br2. This will be giving you 2 Br gas, and the enthalpy will be Br here. But if you have polyatomic, then the case is different. Then we are going to take the mean BDE, mean bond dissociation energy, mean bond dissociation energy for a reaction such as CH4, and it is going to give me, four carbon and 4 hydrogens, right? It is going to give me carbon plus 4 hydrogens, and it will be corresponding to some delta H naught, right? It will be corresponding to some delta H naught of this reaction. Now to write the enthalpy of change of CH bond, we will write that it is equal to delta H naught R divided by 4, because we have how many bonds? We have 4 CH bond, we have 4 moles of CH bond in 1 mole of methane. In 1 mole of methane we have, because we have carbon, hydrogen, hydrogen, and hydrogen. So when we are breaking 1 mole of a substance of methane, when we are breaking 1 mole of methane molecules, in fact we are breaking 4 moles of CH bond, and that is why whatever enthalpy of reaction is this, from going from carbon, that is methane, to carbon and 4 hydrogen, we will divide that by 4 to take the mean bond dissociation enthalpy. Okay, is that understood, guys? Yes or no? Tell me.
Yes, sir.
The two difference, diatomically it is simple, just the bond dissociation energy. But for polyatomic, you will see the enthalpy of the reaction and then divide by the number of bonds that is present in, like for example, CH4 or something, divide by 4. Okay, so let me give you an example. Wait a second, I didn't write this. Let me reshare this thing. Okay. We have a reaction in which we have PCl5. Let us take something else. Let us take SF6. Is going to give you sulfur plus 6 fluorine. So we have done something. So this is corresponds to delta H naught of a particular reaction. This reaction has delta H naught R. Choose the correct relation. You are going to find the enthalpy of SF bond. Okay, enthalpy of SF bond. Yes, which will be the correct option, guys? Yeah, wait a second. It is again not working. Wait a second. Why does this happen? Yeah, which will be the correct option?
C, sir.
C, right?
So C.
Okay.
Yes.
So all of you understood this, right? All of you understood this. Now, we will write the relationship between H naught R and the H naught bond. Okay, bond dissociation energy and the enthalpy of a particular reaction. Enthalpy of a particular reaction. So, right?
Sir, can you scroll up?
Q. Why?
Can you scroll up?
Arey, हाँ, but why?
To write the question.
No, you don't write anything. I will send now.
Sir, but the question you said to write.
हाँ, question, लेकिन ये problem नहीं है ना. This was just a part of explanation. You want to write this like it's very important. solve नहीं करना था ना इस वजह से, because if I'm giving you a question in which you have to solve, then obviously you have to write that. That is why I said that you have to write. Okay. लिखना ही है लगता है अब्दुल रहमान को, लिख लीजिए, आप लिख लीजिए।
Yes, sir, done.
डन, ठीक, ओके सर, आपने कहा था सर क्वेश्चन तो लिखना है सर। फाइन, ओके, रिलेशनशिप बिटवीन enthalpy of reaction and the enthalpy of bond, है ना, bond enthalpy and bond enthalpy. So we will look at a simple, we'll start with a simple reaction and then we can generalize this thing. Okay, so I'm going from A2 to B2, correct? All of you agree? Yes or no? Tell me.
Yes, sir.
So what I'm doing, I'm breaking this bond and I'm making this bond. Yes or no? Tell me, guys.
Yes, sir.
Okay,
Yeah.
fine. I'm breaking this and I'm making this, breaking this and making this. Okay. So all of you know, to break this bond, I need delta H naught AA, yes or no? Because bond enthalpy is defined as what? Bond enthalpy, energy required to break 1 mole of a particular bond, yes or no? So that makes sense. The amount of energy required to break a bond is equal to delta H naught of that bond. Huh, guys?
Yes.
Okay.
Yes, sir.
Yes, sir.
Now, okay. Now making is the reverse of breaking. Making is the inverse of breaking. Yes or no?
Yes.
Yes, sir.
So I can write that for making the BB bond, I will need the negative of delta H naught B BB, because H naught BB, this much amount of energy was required by me when I was going to form it. So the inverse of it, that means the negative of it will be given out, or it will be required, of the heat exchange will be negative of the original one, of the breaking part. Yes or no?
Yes.
Yes.
Okay, okay, fine. That means they are to make.
So why
break
is it
bond.
negative, sir?
Why is it negative? Who is asking? Abdul Sayyid Muhammad. Okay. What are we doing here, Sayyid Muhammad? We are making the bond or breaking the bond in BB?
We are making the one.
We are making the bond. And what does this under the square bracket, what does it correspond to? Only this much part. It corresponds to the energy required for to break the bond. Yes or no?
Yes, sir.
So break का उल्टा क्या हो जाएगा? If I do minus break, that will be equal to make, na?
Okay, sir.
Got it?
Yeah.
Okay. So we can generalize this and we can write that for any reaction, enthalpy of any reaction can be represented in form of the delta H naught, the bond enthalpy of the reactants, minus the bond enthalpy of products. Any problem, guys? Any problem, guys? No, no? No problem with this?
No, sir.
So you can write this part here. Okay, if you want to write, you can write this part, because we are going to use this relationship now. So it needs to be there in your notebook while we are doing questions on this. Let me know if you're done, okay?
Done, sir.
All of you done? Said Muhammad, Abdul Rahman,
Yes, sir. Done.
done? Okay. Right, next question. अच्छा यहाँ पे देखिए आप लोग को like we have three things है ना, we have three things, so you can be, ऐसा नहीं होगा like you will be always asked regarding the enthalpy of a particular reaction in terms of, and you will be given the bond enthalpies. It can be that you are given the enthalpy of reaction and you have been asked the bond enthalpy of a particular substance है ना. So anything can be there, one of the things will be variable, the other things will be given. So simple linear equations in one variable will be this, like the examples, the problems where they are very simple linear equation in one variable. Okay, so let me start with one question. Just on the simpler side, calculate the enthalpy of following reaction. Calculate the enthalpy of following reaction by using given data. By using given data. So the reaction that they have given is, you have this bond CH2 double bond CH2 plus 3 moles of O2 is going to give me 2 moles of carbon dioxide plus 2 moles of H2O. 2 moles of H2O. The data that has been given is, you have been given the bonds. Okay, you have been given the bonds. You have been given the bond dissociation energy. Okay, so you will be given only bond and bond dissociation energy. So the bonds that they have given is, you have been given CH bond. Bond dissociation is 414. All of them are in kilojoule per mole. You have been given the OO bond. This is 499. You have been also given C double bond C. The bond energy is 619. CO bond energy is 724. And the bond energy of OH, it is equal to 460. It is equal to 460. So this is the problem. Now we are going to solve it. So write this problem, and then we will solve this. Let me know if you're done writing the question, okay?
Done, sir.
Okay, so I can write the enthalpy of this reaction is the sum of the bonds broken minus the sum of the enthalpies of bonds formed. So you will, now you have to think in terms of the bonds and not in terms of the molecules. Okay, now start thinking in terms of the bonds. So now you tell me, in this reaction that is given here, this bond here, CH bond, it is broken or is it formed? The CH bond, broken or formed, guys? Broken, all of you? Broken, no? So how you see that the CH bond, it is there in the reactant or the product? I'm only getting one answer. That is why I'm asking again. I'm asking others. Tell me, CH bond is broken or formed by looking at this? Broken, all of you? Broken?
Yes.
Yes.
No one has a doubt, right? So it is broken. Now you have to tell me, okay, fine. We will write the 499, sorry, 414. But how many of this bond is broken? You have to see that also. Because this is when one mole of one mole of CH bond is broken. You have to tell me how many CH bond is broken. Tell me. How many CH bond is broken?
4.
I'm waiting for others also. How many? And how you guys are saying that? How many is broken, guys? Near. Yusra, okay, say something. You want to say something, Yusra? No.
2.
2. Okay. Okay. That means we, first of all, if I will draw it properly, then you will get, na? So you draw it properly. Now you tell me how many. Yes, Khalil. How many CH bonds are there? अरे अब तो बता दीजिए देख के जल्दी. आवाज ही नहीं.
4.
Others, Mehreen, Minashi, Razan, Sayyid Muhammad. Can all of you see 4? Yes or no? Please tell me. That is the only chemistry that I have to
Yes,
teach.
sir.
आगे तो फिर maths है. Tell me, all of you can see 4?
Yes, sir. Yes, sir.
No, I hope all of you can see 4. So I will multiply this by 4. Actually, wait a second. If I had 2 moles of ethene, then I should have multiplied by
8.
8.
8. Okay. Very good. Very good. Now 414 plus, है ना? अभी तो हम लोग प्लस में ही है क्योंकि let us talk about the OO bond. Tell me, the OO bond is broken or it is formed? अरे कहाँ है O2 guys? Formed or broken? Broken ना? Okay, then I will
Broken,
write
sir.
499. Broken. Okay, 499. And I should multiply it with. Okay, Parvati. Yes, I'm waiting for others also. Razan, Minashi,
3,
Mehreen,
sir.
Asia. How much? How much, guys? Once again.
6.
इतना तो धीरे बोलते हैं आप लोग. 3, right? 3. Okay, now you tell me about the CC bond. CC bond is broken or is it formed?
It's broken.
Broken, right? अब हम जल्दी करेंगे. आप लोग तो जवाब ही नहीं देते. And how many? It is broken. So 619. How many CC bond?
So 1.
1. So 619. Okay. Now followed by. Now what about CO bond? It is being formed or broken?
Formed.
Okay, formed. So minus. Okay. 724. How many CO bond are formed?
2.
How many?
2.
2 or 4? कार्बन डाइऑक्साइड के स्ट्रक्चर पता है. देखिए यही तो है. everything is important in chemistry. Everything is important. Molecular structure नहीं पता, enthalpy of reaction नहीं निकल पाएगा. This is carbon dioxide, right? So in one carbon dioxide you have already 2 bonds. In 2 moles you will have 4. 724 into 4. Okay. Now again, next OH bond. Tell me, formed or broken? Formed or broken? Formed. So again minus sign, है ना? Minus sign. Now you tell me, 460 into how many of these are formed? How many OH bond are formed? How many OH bond are formed?
So 4.
Yes, correct. 4. This is the structure, है ना? You have to know how many bonds are there. Now, all of you can calculate this. Yes or no, guys? Tell me. अरे हाँ या ना?
Yes, sir.
हाँ तो फिर calculate कर लीजिए, है ना? Calculate this and tell me. So if it is formed, no matter what, I see the like never go to the reaction. Okay, you go to the data, then to the reaction. Okay, you go to the data and then to the reaction. So if it is broken, then it will be positive. If it is formed, it will be negative. No matter what is the sequence of that is given in terms of this data. Okay. So write this down. Let me know if you're done. I'm getting very different answers. Getting very different answers.
Sorry,
Minashi
sir,
is
my
correct.
answer is wrong.
Minashi, I think yours is correct. Yusra, okay, fine. कुछ थोड़ा mistake हो गया, but it is Razan, you're also correct. Parvati, just make sure, no?
Yes, sir, I made a
Okay.
mistake.
And also Mamuna, आप भी एक बार देख लीजिए. You don't have
Okay.
to, है ना? You don't have to worry about the signs. The signs are fine. You just need to multiply the numbers and then like do the arithmetic. Yes, Sayyid Muhammad, that is correct. Yes, Parvati, correct. And yes, Abdurrahman, correct. Okay, fine. So you're getting the right answers now. No, Khalil, you're doing some mistake. Khalil, you're doing some mistake. No, Mamuna. Mamuna, क्या हो गया आपको? 4 4 are 16. 4 1s are 4. 5. Yes, Mazia, correct. 4 1s are 4 4 are 16. Plus 499 into 3. Rather, I would say 5 दिया 1500. 1500 में 3 घटा लो, है ना? 1500 में 3 घटा लो, 1497 plus 619 minus, this will be 4 4s are 16, 4 2s are 8 and 9, 7 4s are 28 minus 6 4s are 24, 4 4s are 16, 17 18. Now we have 1840 and I can obviously see that it is going to be negative value at least. Mamuna, you got all of same numbers, yes or no?
Yes, sir. But it should that 1840 should be positive, right? Because that
Why?
whole bonds formed is in one bracket and there is a minus sign in front of that, right?
So it should be minus only, ना? ये तो अंदर summation है ना?
Either,
See.
yeah. So sorry, 2896 should be positive.
नहीं. Why?
Sir, you substituted, you gave a minus to both of them, so it's correct, I think.
It is correct only. Like I did not do one step. I hope, Mamuna, you are understanding the arithmetic here. Wait a second. You are saying I should have written it like this. Minus. Then the summation of bond formed.
Yeah.
Sorry. 724 into 4 plus 460 into 4. है ना?
Oh, okay, sir. Yeah, I made a mistake.
है ना? Okay. इसलिए बोल रहे like if you don't even remember the formula, so that is why I was saying whatever is broken that will be positive, whatever is formed that will be negative. Okay. So if you have got the part where you got wrong, अच्छा, I think Khalil also you gave the wrong answer. Did you correct it? नहीं. Khalil, आपकी कहाँ गलती हो रही है?
Sir, calculation mistake.
Calculation mistake. Okay. So just write this down. This will be 964 in minus kilojoule per mole. Yes, Marin, correct. Done, all of you?
Yes.
Okay.
Yes, sir.
Now I'm going to write a few simple enthalpies. Okay, a few simple enthalpies. Then we will be writing. We'll be going on to some different concepts. So I can say that there are some physical transformation that also accompany. They are also accompanied with some heat exchange. For example, enthalpy of vaporization, sublimation, fusion. So all of these are accompanied by some enthalpy change. So I'm just writing this, the enthalpies of physical transformation. Okay, physical transformations. So first is, I should write A part. If a solid is getting converted to liquid, this is fusion, delta H naught of fusion. It is represented by delta H naught of fusion. And if I have a liquid that is getting converted into gas, then it is enthalpy of vaporization. Enthalpy of vaporization. Then if I have solid to directly gas, then it is called enthalpy of sublimation. Easy. Now again here, all of this should be 1 mole. When 1 mole of solid gets transformed or converted to 1 mole of gas to its liquid form, then it is fusion. 1 mole of liquid gets transformed into its gaseous form, then it is vaporization. 1 mole of solid gets transformed into its gaseous components, then it is known as delta H naught of sublimation. Delta H naught of sublimation. Okay. So these 3 simple things, I hope you can remember this, yes or no? Right? Right. Then I'm going to tell you about, no need to write the definitions and all, okay? You just need to know what does it mean. Right, next, that is enthalpy of hydration. We will study enthalpy of hydration. Enthalpy of hydration. Enthalpy of hydration, and it is given by delta H naught hydration. Delta H naught hydration. So in this, we are hydrating a molecule. We are hydrating any chemical substance, and the enthalpy change or the heat exchange between system and surrounding that is accompanied by the solvation or hydration of any substance, that is known as the enthalpy of addition. So this is the enthalpy. The enthalpy change when 1 mole of any gas is ion is hydrated by water. Okay, gaseous ion is hydrated by water. So for example, if you have sodium positive and I surround this by water, then the OH negative, sorry, the OH which has lone pair will be attracting with the positive part, and then there will be some interaction going on here, and this will lead to some enthalpy change. Similarly, if I have Cl negative, then this will have some interaction between the hydrogen atoms, right? The hydrogens of water will be interacting with the chlorine, and hence we can say that there will be some kind of interaction between the iron and the water molecules, and this will lead to an enthalpy change. This will lead to an enthalpy change. Okay, so this is enthalpy of hydration. Right, next, that is more important, enthalpy or the lattice enthalpy. Lattice enthalpy. This is important topic. Lattice enthalpy. Lattice enthalpy. So in lattice enthalpy, we are breaking a solid. So in lattice enthalpy, you must have heard about this in the chapter that is chemical bonding. So this is the enthalpy change. This is the enthalpy change when 1 mole of an ionic compound, 1 mole of an ionic compound dissociates into its ions in gaseous state, okay, in gaseous state. So what we are trying to do, we are trying to have NaCl, that is solid, ionic solid, and if I break this apart into sodium positive, that is a gaseous ion, plus chlorine negative gaseous ion. Okay, now this will be the delta H0 lattice, and this is equal to, for this NaCl is 788 kilojoule per mole. This is shown as delta H0 lattice. Okay, delta H0 lattice. Now, so for lattice energy, what you need to do, you need to break NaCl into its gaseous ions, right? So you have to destroy something, but we don't want to destroy sodium chloride. What we want to say, okay, is there any way that we have some values, right? We have some values and enthalpies already there in the data booklet, right? So can I go from sodium chloride to by various steps and then forms sodium gas and chlorine gas? Is there any way that we can form this? So yeah, there is a way that you can see. So what we are doing, this is our target reaction, this is our target, and then the scientists, they looked up all the enthalpies that they have recorded till now, and they started to pull up the reaction so that we can make this reaction, that is NaCl giving Na plus and Cl negative. This is now our target reaction. So first thing is that how to do this. So we are forming this NaCl is there, and then we are forming Na sodium gas and chlorine gas. So we can write for NaCl, what I can do, I can say that, okay, fine, I will write this reaction. I can have NaCl in the reaction, that is formation of NaCl. If I look at this reaction, so they saw this reaction, that is NaCl, or rather sodium solid plus half Cl2 is going to give me NaCl, and NaCl solid. They find, okay, fine, this is one reaction that is matching one of the components of our target reaction, NaCl. So we just need to reverse this. This is the enthalpy of formation of, this is the delta H0F of NaCl. So what they did, they reversed this reaction, since they got one reaction that is having same thing. So we have written here Na solid, so this will be NaCl giving sodium solid plus half Cl2, and this will correspond to the negative of formation of NaCl. Is everyone fine till here? Yes or no?
Yes, sir.
Yes, all of you?
Yes, sir.
Okay.
Yes.
Then they said that, okay, fine, sodium gas is there, right? Sodium gas is there. So what I can say, okay, fine, sodium positive and there is sodium gas, sodium positive and there is sodium gas. So I can go from sodium gas to sodium positive, and I will call this ionization enthalpy, because we are removing one electron. So this will be delta H0 I, ionization enthalpy from the chapter 3. Yes or no? Tell me. Yes or no?
Yes.
Okay.
Yes, sir.
Now sodium gas. We can prepare sodium gas and we can use this sodium solid giving me sodium gas. Okay, because we need to cancel it now. We need to cancel it. So sodium gas is giving me sodium solid is giving me sodium gas, and I will call this that delta H naught sublimation of sodium, because this is sublimation, correct?
Yes,
Yes
sir.
or no? This is sublimation.
Yes, sir.
Now, next, when I am going and I'm moving towards Cl negative, right? Cl negative. So if I want to get Cl negative, I have to start from chlorine. I will have to start from chlorine. So I will have half Cl2. This is gas. And then I will break this to chlorine. Why I have taken half? Because I need only 1 mole of chlorine. Here also there is 1 chlorine and here also there is 1 chlorine. So I have done what? I have done delta H naught of Cl bond. The bond was there, Cl. I broke those bond and I can just multiply half to it, because what I have done, I have written the reaction in terms of half mole of Cl2. So if delta H naught Cl is the bond dissociation enthalpy or the bond enthalpy of 1 mole of Cl2, then for half I will just multiply by half. Yes or no? Any problem, guys? Any problem?
No, sir.
No. Now we have got the chlorine gas. So what I will do? Chlorine gas, I will add 1 electron and I will say that this is chlorine negative gas, and I will call this electron gain enthalpy from the chapter 3 that we have learned, periodic properties. Electron gain enthalpy. Yes or no? Yes or no, guys? Tell me.
Yes, sir.
We can do this, right? So what we have done till here, so if I will add this complete reaction, if I'm adding this reaction, then what I'm getting? See, NaCl is there, so I will write NaCl. Then there is sodium solid, so I can cancel this sodium solid by this sodium solid. I have this half Cl2, so I can cancel this half Cl2 by this half Cl2, correct? Then I have sodium gas. This sodium gas can also be cancelled by this sodium gas. This chlorine gas can be cancelled by this chlorine gas. So the only thing that is remaining with me is sodium chloride is going to give me sodium positive gas plus chlorine negative gas. Now this is what we call delta H naught of lattice, and it is the sum of all these energies. Yes or no? It is the sum of all these energies. Yes or no, guys?
Yes.
Yes.
This is the sum of all of these energies. So this is what we have done. Now we can look up all of these values from the data booklet, and even if we have small values, then we can calculate and tell the enthalpy of lattice enthalpy of NaCl. So I can write the delta H naught lattice will be equal to the minus of, so minus को बाद में लिख लेंगे, है ना? Let us write the positive parts first. So delta H naught Eg of what? Of chlorine plus half of delta H naught of chlorine bond plus the delta H naught of sublimation of sodium plus the delta H naught of ionization minus the H naught formation of NaCl. Minus the H naught formation of NaCl. Okay. So all of you understood this? Yes or no?
sir.
This is known as the Born-Haber cycle. This is known as the Born-Haber cycle. So let me just pull up an image from internet that is better representation than whatever I am going to draw. Okay, so these are the same thing. So what we are doing, we are having the delta H naught of formation and then the delta H naught sublimation of sodium to gas, then to sodium chloride, and then we have delta H naught dissociation, and then electron gain enthalpy. It's all of these things, and then this is going to form NaCl. So if I just reverse this, then it will give me the lattice energy. Okay, so the same thing that they have done, they have just represented this in terms of a particular image here. Okay, so that is a kind of cycle you can make. You can make your own cycle. This is not, I mean, you can tinker a bit, you can move things here and there, but at the end it should represent the correct thing. Okay, so the best way I think is this particular flow of reactions, and it is very much representative of the Hess law that we have learned just now. Okay, so this is lattice enthalpy. This is lattice enthalpy. You may be asked this directly. Give me the reaction for the calculation of lattice enthalpy of sodium chloride. Then you will have to write all of these reactions. Okay, you'll have to write all of these reactions. So I will not ask you to memorize this. What I will say is that you just try to write this 10 times, logically explaining it on each step. Since I need a sodium chloride in the reactant side, so I'm going to write the formation of sodium chloride in the reverse reaction. Then I need sodium gas, so I will start with sodium solid, then I will convert it to sodium gas, then from the gas I will remove one electron. So I'm doing sublimation and then ionization. Similarly for chlorine gas, how I will get Cl negative? I have to start with half Cl2, then I will convert it to chlorine. So I'm breaking the Cl-Cl bond. Then in chlorine, I'm adding one electron. If I'm adding one electron in chlorine, I'm getting chlorine negative. So that is why I'm getting delta H naught Eg. Okay, so if you write this at least 2 or 3 times only, so then you will be able to write any type of lattice enthalpy. Okay, any type of bond Cooper cycle. Okay, so next thing that we want to learn is the enthalpy of solution. The enthalpy of solution. Enthalpy of solution. So this is the enthalpy change. The enthalpy change when 1 mole of substance gets dissociated in a specific amount of solvent. Specific amount of solvent. Okay. So what happens? You will have some AB solid and you will put that in water. Okay, and you are going to get A plus aqueous plus B negative aqueous. So this is the delta H naught of solution, enthalpy of solution. I can say that first of all, AB solid, it gets dissociated into A positive gaseous state plus B negative gaseous state. This is the delta H naught lattice, and then further they get hydrated by water, and this can be represented as the delta H naught of hydration. This can be represented as delta H naught of hydration. So I can write, rather I can rewrite the enthalpy of solution, delta H naught of solution. So if I have the lattice enthalpy of a particular substance and the hydration enthalpy, then I can easily calculate the H naught of solution, the enthalpy of solution. I can easily calculate the enthalpy of solution. Okay, right. The next part, that is the enthalpy change when you are enthalpy of dilution, when you're diluting something. Enthalpy of dilution. Enthalpy of dilution. So this is the enthalpy change the enthalpy change when specific amount of solute, when specific amount of solute is added to specific amount of solvent, specific amount of solvent. So starting, if I have very little, I have very little water molecules. Okay, I have very little water molecules, and I have added much of salt. I have added much of salt. So all of the salt dissolved, and there was some salt that is remaining even now. So what I did, I diluted this solution. So I added some more water. Okay, now at this point of time, all the salt or sugar, it got dissolved. Okay, that means more and more salt or sugar, more and more of solute particles, they were getting dissolved, and hence I can say that the enthalpy was increased, right? The enthalpy of dilution or the enthalpy of solution, it was increased. But if I add more water, then I can say, okay, fine. Now the solute particles, it has more water to interact with. But the increase will not be much significant. If I keep on diluting, then I can say, yes, now the solute particles, it has more particles of solvent to interact with, and then the enthalpy must be increasing. But at the end, it will approach a value from where it cannot go more. So it will approach a limiting value. And from that limiting value, it cannot rise more. It cannot rise after that value. As you cannot dissolve anything and keep on diluting. So we can write on successive dilution. The enthalpy change approaches a limiting value. It is approaching a limiting value. Okay. So this is all about the thermochemistry part. Okay, so we have done many things on the enthalpy. So if I just want to revise everything, so we started with thermodynamics. We started with some derivation and some definitions: system, surrounding, process, thermodynamic equilibrium, right? In process, we have many parts that we learned, right? Then we also did some new definitions like internal energy, U. Then we wrote about heat, we wrote about work, and a few important things regarding the heat and work was the delta U. It is equal to the heat involved and the work involved in a particular process. Now, this is a general equation, which is a mathematical representation of the first law of thermodynamics. Then what we had delta U. We also saw that delta U was equal to Q minus P delta V, because we wrote W was equal to minus of P delta V. Then we got some different specific. We had some specific ways of writing this. If I had isochoric, if delta V was equal to 0, then I wrote that delta U, it is equal to QV. Yes, okay, Yusra, fine. Then if we said that if Q is equal to 0, in isochoric process, if the temperature it is equal to 0, that means what is happening? There is free expansion. If free expansion is taking place, when P is equal to 0, then also delta U will be equal to Q. Now, the two most important ones were delta U was equal to QV, that means at constant volume, and delta H was equal to QP at constant pressure. So these are the two main things. Then we wrote the relationship between delta U and delta H, and there were two relationships, right? So first we had delta H is equal to delta U plus P delta V. We also had delta H is equal to delta U minus delta NGRT, right guys? Minus delta NGRT. Next, what did we do? What did we have next? We learned about Hess law and all, right? Yes or no? Right, guys? We learned about Hess law and enthalpies, right? So Hess law is important, that we learned today only, so I won't write anything. And then we also learned about the bond. Two important. Delta H naught of reaction, it is equal to delta H naught of formation of products minus delta H naught of formation of reactants, and delta H naught of reaction, it is also equal to the sum of bonds broken minus bonds formed. Okay, so these are two most important equations. Next, we are again going back, and we are going a bit back towards the thermodynamics parts. Okay, so this was thermochemistry. Now we are going back towards the thermodynamics part, thermodynamics. So in thermodynamics, we were talking about the transfer of heat or flow of heat. Okay. Now we want to say, we want to answer the question, why does anything happens? Why does anything happens? Okay, so if I start with a simple analogy, I will say that this is a pen. This is a pen. Okay, this is a pen, and this pen is at some h height above. This is my ground, and it is h height above. So what will happen? It will fall down. It will fall down, and it will remain here. So first thing is that if something does not want to stay on its place, if something is moving or if something is changing, then I will say that it is not stable, and that is why it is changing its situation. Am I right with this? Yes or no? Tell me. If some change is happening, that means the system is not in its most stable form. That is why it is moving towards its most stable form. Yes? Yes or no?
Yes, sir.
Yes, sir.
Yes.
So, and now I will relate stability. So everything wants to attain its most stable state. Yes or no? Everyone is okay with that?
Yes.
Yes, sir.
Yes, sir.
Each substance wants to attain most stable state, most stable state. Okay, and that is why when this pen had some potential energy when it was at h height, and when it had fallen down and it is at rest right now, so the potential energy is decreased, and it is equal to how much? It is equal to 0. So we can also relate, we can say that stability is inversely proportional to energy. Right, guys? Yes or no?
Yes.
Yes. Correct?
Yes, sir.
Okay. Now we will try to answer. Everything in terms of this very basic statement that stability is inversely proportional to energy. So if the energy of a system is decreasing, then stability is increasing. And anything that is happening, it is happening only to increase the stability. So the energy of a system should always decrease if anything is happening spontaneously. So remember this word spontaneously, it means it is happening automatically. So if I'm dropping the pen, automatically का मतलब ऐसा नहीं कि like there is no physical law existing. है You will say, sir, automatically pen is falling down, so gravity is acting on it. Yes, the gravity is acting on it, but no human is doing any work in order to make the pen fall. So when I say automatically, I mean naturally. I mean that he does not have to put in any energy for that process. So you are okay with the spontaneous, and you now know how we are using that word automatically and spontaneous. Yes or no? You're okay with this?
Yes.
Okay, so spontaneous, it does not mean that no physical force. It means for some physical force will be there, but that will be a natural physical force. No human is doing any work, or he is not putting in any energy. He's not putting in any energy for a process. So falling of pen is automatic. It is a spontaneous. Yes or no? Falling down of pen?
Yes.
Yes, it is spontaneous. Okay. Now, tell me about this situation. tell me about this situation. I have a box. It is completely isolated. Okay, so the isolated means heat is not going to exchange. Heat is not going to be exchanged from this system that we have made a system here. Okay, heat is not going to exchange. Now it will not go away. It will not be taken by the surrounding, and no heat will be taken by the system from the surrounding. The heat exchange will be 0. Q is equal to 0 between system and surrounding. But here we have, use this part now. Here we have two blocks, two metallic blocks. Here we have two metallic blocks. One of them is at 100 degrees Celsius. The other is at, let us say, 0 degrees Celsius. It is at 0 degrees Celsius. Okay. Now I want to ask you what is going to happen if I make both of these blocks and I make them touch. So they are touching each other. So after a long time, this is block A, this is block B. So after a long time, what will be the case? What do you think? That it is not 850 exact value. Yes. Okay. Okay. Fine. Yes, I'm thinking more of you can answer this question. What will happen after a long time? Okay. Fine.
Sir, can you repeat the question?
What will happen after a long time? We have touched A and B blocks. A is at 100 degrees Celsius and B is at 0 degrees Celsius. After a long time means after a very long time. Jitna long aapko sochna, utna long aap sochiye. It is an isolated system. So no heat can go away from the system. It cannot go out of the system. So which of the option? So I think you guys, those who have answered, they are pretty confident with their answer, right? And that is the right answer, those who have answered. That is going to happen. But I'm hoping for more answers. Mehreen, Sayyid Muhammad. They are metallic blocks. Let us say copper or iron. Okay, Muhammad, can you explain your answer? Yes, Muhammad.
So they are isolated. So like between
The
both of
system is
them.
isolated, na? Yeah, isolated, na? हमने तो box बनाया हुआ आपको.
Oh, that is isolated. The wall in between them, sir.
This is system. This is our system. This is not like system के बाहर कुछ होगा ना. It's not wall. It's a block. It's not a trick question, guys. Mohammed, it is not a trick question. ऐसे simply आप सोचो ना, हमें डब्बा दिया, उसके अंदर दो ब्लॉक को टच करके रख. Yes, not if you want to change the answer, Mohammed. Okay, fine. So all of you are confident about C, yes or no? All of you are confident?
Yes.
Yes.
Okay.
Yes, sir.
Yes. Okay, fine. So something is happening, a change is happening. I can say that, yes or no? When I'm touching of these two things, so there is an initial and there is a final, and there is a difference between those two things, right? Correct?
Yes.
Why is that happening? We have a system. In that there is some energy. Right? The energy of the system is not changing, na? Because the heat is not leaving the system. Yes or no? Is the heat leaving the system?
No, sir.
No. But still there is a change happening without any change in the total energy. So why is that happening?
So to reach stability.
The thermal
So is
equilibrium.
Due to
stability. But
temperature difference.
yes, Mohammed, what did you say? I could not hear that, Mohammed.
Due to temperature. To attain
Due to-
stability due to the temperature difference.
Yeah, it is fine. I understand that this temperature difference. Okay, but again, the question is our system. That means you are saying our system is more stable when both of these blocks of metal, they have the same temperature, around same temperature. Yes or no? You're saying that?
Yes.
Yes, sir.
Okay.
Yes, sir.
But can I say if I start with the initial, if I start with initial and go to final, then can I say that the total energy inside the system will be same only, na? So there is
Yes.
no, so system is not losing energy, but still it is gaining, stability, right? So our idea of stability is incomplete. Like you can see the energy is, nothing is happening to the energy. The energy is not changing, but it is still gaining energy. Sorry, it is still getting stable. It is still gaining stability without any change in energy. And hence I can say this, our initial proposition of stability is inversely proportional to energy is incomplete. Yes or no?
Yes.
Yes.
Because we can't explain why is this happening with this simple idea of stability is directly proportional to, sorry, inversely proportional to energy, right? We cannot explain it. Or if you want to take some time and try to think, I can give you 2 minutes. You can think about it. Similarly, also let me tell you of one more very easy example. Okay, very easy thing that I think we should think about. Let us think about evaporation. Think about evaporation. What happens in evaporation, guys? What happens in evaporation?
Liquid gets converted into gas.
Liquid gets converted into gas. Can you elaborate this and explain how does this happens?
Liquid gets converted into vapor just below its boiling.
Sorry, what did you say? Boiling?
So below its boiling point.
Below its boiling point. So why does this happen? We know now. Actually, you are saying that there is water and water is getting into H2O gas, but the temperature is 25 degrees Celsius. So at 25 degrees Celsius, this water should be in liquid state. Yes or no?
Yes, sir.
Yes, sir.
But it gets converted into gas. And also, you know that if I have something liquid and it is getting converted into gas, that means this liquid, it has lower energy. Now this gas will have high kinetic energy. It is moving here and there, the complete universe, it can move to the complete universe, and it has higher velocity. Something is having higher velocity, so it is going from lower velocity to higher velocity. So what the water is choosing, the water is choosing to be in more highly energetic state rather than less energetic state. Yes or no?
Yes.
And that too, are we giving it enough energy? Tell me. Kya chahiye? Like if I want to convert liquid to gas, water, then I have to increase the temperature of liquid to 100 degrees Celsius. Yes or no? Right?
Yes, sir.
Okay, so now there may be some people who may be thinking like this, that there was water यहाँ पे था. Sir, आप कैसी बातें कर रहे हैं? तुरंत ही ना boil होता है. उसने क्या किया? Environment में ना, we had 25 degrees Celsius as environment. So it is taking heat from the environment, taking heat from the surrounding, and then it is reaching to 100 degrees Celsius, and then it is evaporating. Is there anyone who thinks like that? That this can be a reason why the water evaporates?
Sir, I
Yes,
thought
sir.
so.
You thought so. So can you see that this thinking is not very valid, and why it has some, like, I can see there is some gaps. So see, first of all, that this water cannot go higher than 25 degrees Celsius, because the surrounding is 25 degrees Celsius. अगर ये बताइए आप water है and this is 100 degrees Celsius, then the heat will be going from water to the surrounding. Na? So I can say for sure, if you're not heating it, the surrounding is 25 degrees Celsius, then it cannot have energy, it cannot have a temperature higher than 25 degrees Celsius. And another thing is that if something is evaporating and there is water spilled in the floor, ऐसा नहीं है ना कि 5 मिनट बाद छू के देखते तो वो गर्म हो जाता है. Does it happen like that? Does it get warmer?
Yes.
No, no. It doesn't get warmer, right? It doesn't get warmer. What happens? So I can say that the temperature is obviously not rising. And so the temperature of the water that is getting evaporated is obviously not reaching 100 degrees Celsius. Correct?
Yes, sir.
So we have established that the water that is getting evaporated is not reaching 100 degrees Celsius. Okay, it is not reaching 100 degrees Celsius, but still water, what a fool, he wants to be in the state of high energy. It wants to be in a state of high energy rather than liquid, which is lowest, which is more stable, which is having less energy. So our idea of stability and our idea, the whole idea of why anything happens and as common as evaporation is not explainable only if I use this term that is energy. So we have some gap. We have some gap in our science that we have to consider. And now let me go back to this part. Now, before going to this part, maybe I have told you, maybe I have not discussed this with you. But if you can remember something vaguely like this, okay. So does anyone remember what I have drawn? So that means you guys have not studied electronics. Yes, Yusra, you remember?
I guess.
You guess? Okay. Now I have, this is a coin. This is the example that we do when I teach you guys electronic structure. That I use this, and this is our Earth. Okay. This
Oh
is our
yes,
Earth.
sir, I remember it now.
You remember it. Okay. So I think Razan should also remember it because I think she had studied electronic structure, atomic structure with us. Okay. And what I have done, I have charged this coin. हमने इसका क्या किया? Potential increase कर दिया. I have increased the potential of this charge, and I have charged this to 1000 volt, and I have charged the Earth to 1000 volt. Okay, guys. Khalil, Mazia, Mehreen, Minashi, Parvati. You are understanding the situation? You are understanding the situation? Yes. Now you tell me, what will you touch? The A situation or the B situation? Are you ready to touch the coin or rather touch the Earth? Which will give you more shock? Yusra नहीं बताइए, आपको तो पता होगा. I'm asking these guys, new Khalil, Mazia, Mehreen, Minashi. What do you think, A or B? So Khalil, what are you saying? Which will give you more shock, or what are you going to touch? What are you going to touch?
So I would touch B.
You will touch the Earth. What
Yes.
about others?
B, sir. B, sir.
B?
Sub B.
B? B. Okay. Now I'm asking you a different question. All of you want to touch the Earth. Huh? No one wants to touch the coin. So see, inherently, na, आप देखिए, like how your mind is there. Your mind knows the answer. So even though you have not studied it, but your mind and like how this brain has developed the prefrontal cortex is it knows what is less dangerous to us. And now tell me, what situation would you rather be in? Tell me, A or B? Which situation?
B, sir.
B? Obviously B.
Yes.
Yes.
Yes, all of you. Anna, see, your mind knows that I am going to choose. I am going to
Yes, sir.
choose a situation where I am getting less hurt. So I can say, which has more energy, A or B? A or B, which has more energy? A or
So
B?
A.
A.
A has more energy. But
A.
here the energy is same, but still, Anna, here the energy is same because we have increased the potential to the same 1000 volt, but which one is going to give me less shock? The earth is going to give me less shock. है ना? Why? Because rather than energy, rather than the charge, है ना, what is more useful is the density. Density means a particular charge or the energy that you have, it is situated in a smaller region, it is situated in smaller volume, or is it situated in a larger volume, So obviously 1000 volt in here, I can say the charge density or the energy is concentrated in a coin, and here it is diluted in the earth. That is why this is more stable, and that is why I want to touch that, because the change will not happen. So देखिए क्या होता है, like when you are getting shocked, something is happening. So your body, it does not want anything to happen if you are touching something. So what does it do? It chooses the earth, because it knows if I am going to touch the coin, something is happening, and that something is going to be harmful to me. That something is going to be harmful for me. So that is why it is choosing the earth. Why? Because nothing is going to happen. And if nothing is going to happen, that means it is already in the stable state. Rather, when you touch the coin, something will happen and you will get the shock. That means a change is happening. And hence I can say that coin is having higher energy density. And I can say which is more stable. Earth is going to be more stable. Okay. Fine. All of you understood this? Yes or no? Now let us move on to this part. Now, when I look at A and B, I can say that initially all the energy is concentrated in the A block. So what happens if you have any system, it wants to do what? It wants to spread out its energy. So what it can do? Now it can flow the heat from the higher temperature to the lower temperature. So even though the total energy is going to be same, but the energy density is going to decrease. The energy is now available in a larger volume, and hence it is more stable. Yes or no? Tell me, guys.
Yes, sir.
You got it?
Yes, sir.
So one thing is energy, the another thing is dispersion of energy. So if you have any system, it wants to disperse its energy as much as possible. Okay, so what does it want to do? It wants to do what? Disperse the energy. It wants to do what? Disperse the energy. Okay. Now, I hope you can understand why the evaporation happens. Here the liquid is present, right? The water is present, and the energy is concentrated, right, in a very smaller volume. And now think about the gases, particles, H2O, that has the ability to wander the whole world, the whole atmosphere. So the volume is infinitely increasing. And hence it rather wants to evaporate slowly. And if you give it enough time. Now you please remember, when I started equilibrium, I said that we are not going to talk about time. We will think that we have ample amount of time. So at the end, what is going to happen? If you just leave the water like this, all the water is going to evaporate. Now the next thing that I want to talk about is the universe. We initially said that universe is an isolated system. Yes or no? Universe is isolated. Now when universe is isolated, it means there is not even a surrounding. So I can't talk about the energy, right? I can't talk that energy will leave out the system, or the energy is decreasing in the universe, or the energy is increasing in the universe. I can only talk about the energy dispersion. I can say that anything that happens in universe, it should lead to, if something is happening in universe, it should lead to the energy dispersion. So what should happen if something is happening inside the universe? Then in universe, what should be present? In universe, the energy should be constantly dispersing. So energy should be dispersing, and it should be getting a higher and higher volume. It should be getting a higher and higher volume. And the measure of this thing, that is energy dispersion, it is known as entropy. You guys have heard about entropy previously? Yes or no? Ever heard of entropy? Huh? You guys have never heard of entropy? अरे yes or no तो बोल दीजिए, यानी कि नहीं हुआ. Thermodynamics is not done in your school?
Yes, sir.
Not
Yes,
done.
sir. Heard.
No, sir.
Thermodynamics is not done. So those who have done thermodynamics, I hope now you guys have a better understanding of entropy and what entropy tries to say. Yes or no? So whatever the NCERT has written, like it is the measure of disorderness, it is the measure of randomness, it is the measure of this and that, just leave that to the textbook. It doesn't make sense to me. It does not make sense to me in 11th standard. Neither does it make sense to me now. Entropy is the measure of energy dispersion. Okay. Entropy is what? It is the measure of energy dispersion. So now this is going to be true everywhere. This is going to be true everywhere. Okay. So I'm leaving you guys right now with this entropy. We will meet after 1 hour. We will meet after 1 hour. That means you have 10 minutes right now. So I can say, what is the time now, guys? There.
6:21, sir.
कितना हो रहा है? 8:21.
6:21.
6:21.
Yeah, same here.
Sir, everyone, sir.
हाँ everyone.
Okay, sir.
हाँ, तो जिसका भी जो भी हो रहा है ना, तो वो या तो मतलब 1 घंटे बाद मिलेगा, but not 21, 31, 30 पे, है ना? 1 घंटे बाद. Take the round of time. Okay. So then we will start like writing equations and quantifying things, because now you understand, right? Now we have everything with us that we can tell why anything happens in universe. And if you say chemistry does not have any real life application, I am telling you guys why anything happening in universe. I hope you are not getting this in physics. Okay? I hope you are not getting this in physics. What we are learning, why anything happens in universe. More on that after 1 hour. Thank you guys. Thank you very much.